Dr. K. Parinivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Hello, welcome to the lecture series on chemistry of environment. The previous class we discussed about atmospheric chemistry and discussed about smog, especially in the photochemical smog formation and the effects and how to control it. And today we are going to discuss about yet another air pollution episode, namely ozone layer depletion, that is stratospheric ozone layer depletion. Just to tell you the background about ozone, chemically it is consisting of 3 atoms of atomic oxygen combined together to form ozone molecule. This is relatively a stable molecule, but it is highly reactive oxidizing chemical. The word ozone is derived from the Greek word ozone, that means to smell, and has a strong pungent odor. In fact, we can recognize a smell by the slightly fishy odor wherever it is there. Definitely it is associated with ozone, especially in the near the transformer, electrical transformer, we can notice this. And these electric discharges significantly produces ozone. That area, that smell is an indication that ozone is present in that area. If you look at ozone, we have both good and bad ozone. In the introduction class itself, I told you ozone is present in the stratosphere, and the significance of atmosphere also we discussed. It protects the earth from harmful effects of UV radiation, because it absorbs a light and protect us from the adverse effect of this UV radiation comes from the solar light. So, in this way this is considered as beneficial and good ozone. On the other hand, suppose ozone is present in the troposphere, that is the layer close to the earth, it is considered as bad one, because it is likely to cause respiratory distress and eye irritation. And also earlier also we discussed it destroying the plants and producing cracks in the rubber, because rubber molecule consisting of isoprene, it is a double bond. Ozone likes to react with this double bond and form ozonide, ultimately leading to the crack and deterioration of the material. So, in that way ozone present troposphere considered as a pollutant. However, it is a very strong oxidizing agent, reacts with any double bond containing compounds forming epoxide and ultimately leading to further reaction. So, ozone present in stratosphere is beneficial. Because of this, it absorbs the harmful UV radiation, whereas if it is present in the troposphere, it is considered as a bad ozone. And this also already stressed, the diagram clearly indicates again the different layers, how the atmosphere is classified. And you can see here the ozone is present in the stratosphere concentration. Okay. It is not very high, even in the stratosphere about 10 ppm, and but that is very, very important to filter out all the harmful UV radiations. And this is a UV absorption spectrum of ozone. You can see clearly ozone absorbed around 250 nanometer in the UV region, and that is why it filter out all the harmful radiation that come from the electromagnetic spectrum. Ozone in the stratosphere absorb this harmful UV radiation and filter, so that whatever the remaining electromagnetic spectrum reaches the earth atmosphere or the lower part is free from the harmful UV radiation. So, next we are going to see how this ozone is formed in the atmosphere. In the previous introduction class itself, I told you the formation of ozone, how it is happening in stratosphere, the reactions are given again for the clarity again. Nitrogen dioxide is capable of absorbing light, especially with less than 400 nanometer, and produce or causes a dissociation to form nitric oxide and atomic oxygen. This atomic oxygen formed is highly reactive and combines with the molecular oxygen and form ozone molecule. So, this ozone is formed. So, this NO, that is nitric oxide, can react with ozone to form NO2 plus O2. The NO2 again, these two equations already given here, ozone and the nitric oxide formed can react with this hydroperoxyl radical as we discussed before and forms again NO2 and hydroxyl radical. And this NO again can react with alkyl peroxyl radical again similar to the hydroperoxyl radical and forms NO2 NO2. So, the net result is always ozone is formed in the stratosphere as per this equation, and you can get ozone formation in the stratosphere. And usually, as I told you, the concentration of ozone is present in the atmosphere or stratosphere about 25 to 35 kilometer range. The concentration is roughly 10 ppm, and usually the ozone concentration is expressed in the present in the column, that is total column of ozone is a total amount of ozone integrated from the surface to the top of the atmosphere. That is normally referred as total column of ozone and expressed in Dobson unit, named after a popular scientist who worked pioneering work in this field ozone and GMP Dobson. And one Dobson unit has a thickness measured in units of hundreds of a millimeter, that is 0.01 mm, that the ozone column would occupy at standard temperature and pressure, that is 273 Kelvin, and 1 atmosphere is 1 Dobson unit, that is measured in units of 100 of the millimeter, 0.01 mm, that is normally 1 Dobson unit. And generally in the stratosphere, the total ozone column values, if we measure it, it ranges from 290 to 310, which is considered as normal. Okay. If the ozone column lies in the range 290 to 300 Dobson unit, it is fine. But if all the atmospheric ozone were brought down to the earth's surface at standard temperature and pressure, it would produce a layer of about 3 mm thick, that is the total entire global atmospheric concentration of ozone. This is normal. And what is ozone depletion? Suppose when some of the ozone over height is lower than the 2/3 of the normal value, from this 290 to 310, it is 2/3 is lower to 2/3 of this value, then it is called ozone depletion. Okay. And ozone layer in the stratosphere is depleted, almost harmful radiation consisting of UV will reach the lower atmosphere. And scientists who conducted research on this ozone concentration in the atmosphere, they have found there is a hole is formed in the stratosphere, especially in the British Antarctic survey team has measured the ozone level and noticed there is a disappearance of ozone from the stratosphere. There is monitoring data by this British team indicate that the column ozone level have been decreasing since 1977, and this observation of decreasing ozone concentration was also later confirmed by satellite data. One satellite advancement was used for monitoring data. This was also confirmed again by the satellite data, that is total ozone mapping spectrophotometer was used, and they also confirmed there is a loss in ozone in the stratosphere. Okay. But this was not accepted by some group of scientists. Initially they thought the satellite data may be something wrong with that, that is why it giving a value lower than the 190 Dobson unit. Normally it should be around close to 300 Dobson unit. So, this may be something wrong with this resolution of the satellite or something, but later again it was confirmed, and there is ozone depletion is taking place in the stratosphere. What are the reason for this? So, scientists working on this, they have calculated what could be the reason on this thing. They have come out with the 3 postulations. One is chlorine and bromine containing compounds, other one is hydroxyl radical and nitric oxide. All the 3 hypotheses were proposed for the destruction of ozone in the stratosphere, and especially in the predominant one is chlorine route. The nitric oxide and hydroxyl route, of course, it is happening in the atmosphere. The hydroxyl radical formed may destroy the ozone in the stratosphere. As per this one, the hydroxyl radical can react with the ozone, forms hydroperoxyl radical. This formed radical may react with atomic oxygen, that is also considered to be ozone, and converts into molecular oxygen, which is a less reactive species, where atomic oxygen can combine with the molecular oxygen to form ozone, as we discussed earlier. So, there is a, if there is atomic oxygen is there, it can combine with ozone and forms 2 molecules of oxygen. So, there is a loss there due to hydroxyl radical also. Similarly, nitric oxide present in the atmosphere also can bring in reduction in the concentration of ozone. Nitric oxide can react with the ozone and forms nitrogen dioxide plus molecular oxygen, and the nitrogen dioxide can react with the atomic oxygen, forms molecular oxygen and nitric oxide. So, the net result is again atomic oxygen can react with the ozone to form 2 molecules of molecular oxygen. In both the cases through hydroxyl radical and nitric oxide, ozone depletion is taking place. But the more important one is the chlorine and bromine halogen containing compounds route. Okay. If chlorine and bromine containing organic compounds are exposed to strong UV light, normally happening in the upper part of the atmosphere, what happens is chlorine radical will be generated. This radical species is one of the highly reactive species, can react with the ozone and forms chlorine oxide radical species. Okay. This in turn further reacts with the atomic oxygen, can generate chlorine radical again. So, this is a kind of a catalytic process. You can see there atomic oxygen is reacted with molecular ozone and forms 2 molecules of molecular oxygen. This is a chlorine oxide cycles. So, all the 3 routes are possible for the destruction of ozone in the stratosphere. Predominantly the chlorine route comes from this chlorinated and brominated organic compounds, that is result of human activity. How it is happening? The main source is photolysis of chlorine containing compound. Suppose any CFC compound, chlorofluoric compounds, reaches the stratosphere where strong UV light is available and can initiate the photochemical reaction. That is radical generation, chlorine radical will be formed, and this is yet another reaction, and if it is chlorine is generated from this compound also. And so, any chlorofluoric compounds reaches stratosphere because of the strong UV light, get exposed and initiate photolysis reaction forming chlorine, that already we discussed. If you go and see here, it consumes the ozone present in the stratosphere, and most of the CFC compounds, because of the human activities, we use all these CFC compounds for various purposes, including refrigeration, cooling, all this, and ultimately these compounds reaches stratosphere slowly. In the troposphere, they are considered to be a long lived organic compounds, no reaction, nothing will happening. Slowly it get into the stratosphere, move into the stratosphere where a strong light is available, and that is sufficient to initiate these type of chlorine radical formation species. So, mainly all the CFC compounds is due to the human activity. We use this compound, as I told you, for cooling purpose, refrigeration, all those things that slowly escape into the atmosphere or troposphere, and then ultimately reaches where it reacts, generate chlorine radical and reacts with the ozone, destroying this. Also naturally there is a possibility of methyl chloride from biomass burning, it is also possible, that also bring out this depletion of ozone. So, both man-made CFC compounds predominantly, and naturally if you burn any biomass, that may lead to methyl chloride. Any chloride compounds are there that will combine, and ultimately methyl chloride may be formed, that also escape into the top of the atmosphere and generate these type of radical species generation due to photolysis and bring out ozone depletion. One possibility of a chlorine termination reaction is, suppose chlorine is there, if it reacts with methane, if it is present, definitely the chlorine is converted to hydrochloric acid and stop or terminate this reaction of generating or destroying, generating radical and destroying chlorine. And similarly, the chlorine oxide may also react with the NO2 and form chlorine nitrate. This also generate ClO species, earth reaction ClO, and the moment it is exposed to UV light, it will generate ClO and nitrate, and that is also will destroy ozone. These chlorine radical species formed can be terminated and bring a halt to this ozone layer depletion. That is, methane is one species, it can react with this chlorine radical and generate methyl radical, bring a halt to this chlorine by converting chlorine radical into hydrochloric acid, and that is a stable compound in the stratosphere. And similarly, chlorine oxide species can react with the nitrogen dioxide and form this species. This also considered to be a relative unreactive species and bring a halt destruction of ozone in the stratosphere. And similarly, nitric oxide also remove the process, that is, it is produced abundantly in the troposphere, but all of this is converted into nitric acid and removed through precipitation as acid rain that we are going to discuss separately. And NO in the stratosphere produced from the nitrous oxide N2O, which is much less reactive than nitric oxide. So, the nitrous oxide will be converted into nitrogen plus oxygen, that is, this is a reaction contributing to 90% in the stratosphere, and nitrous oxide can also react with atomic oxygen to convert into 2 molecules of nitric oxide. This possibility is about only 10%. The removal process, if you look at it, the NO2 can react with the hydroxyl radical and form nitric acid, and similarly chlorine oxide radical can also react with this nitrogen dioxide, form this chemical species and bring a inhibit action to this ozone layer depletion. And in fact, if you see the nitrogen oxide, they have two-sided effect, that is, NO provides a catalytic chain mechanism for the ozone destruction, because we have seen there are 3 ways it can generate or bring out the ozone. One is through nitrogen oxide route. Also, it inhibit the oxide to nitrogen, inhibit the hydroxyl radical and chlorine oxide species for destruction of responsible for the destruction by removing radical species in the 2 cycles. Okay. So, both it acts as a chain as well as inhibitor. So, the oxides of nitrogen contribute in 2 ways, and the relative magnitude of the 2 effects is altitude dependent. So, about 25 kilometers above, the net effect is to destroy ozone in the present in the stratosphere. That is, NO accounts for about more than 50% of the total ozone destruction in the middle and upper troposphere. This is a main thing, whereas in the lower stratosphere the net effect is protect ozone from destructions. So, the oxides of nitrogen have 2 effects. One is the catalytic chain mechanism, as we discussed before, the other one is inhibit the cycle formation through this hydroxyl and chlorine oxide radical. The catalytic destruction reaction describe chlorine route or nitrogen oxide route or hydroxyl route account for the absorbed average level of stratospheric ozone, but they are not able to explain the Antarctic ozone hole, whatever the average concentration, they are unable to account for this ozone hole over Antarctic. This is a phenomena. First, it is actually called Antarctic ozone hole. As we discussed before, it all air pollution episode goes with the place name, London smog, Los Angeles smog, etc. Similarly, here the ozone hole is also popularly called Antarctica, because this hole was first observed in the Antarctic region. The ozone depletion in the Antarctic region is limited both regionally and seasonally. This is a special point to be noted for, especially for Antarctic region. The depletion is too great and too sudden, and this observation cannot be explained by catalytic ozone destruction by chlorine oxide route alone. There is a sudden loss in the ozone in the Antarctic region. We will see why. Ozone depletion occurs at altitude between 10 to 20 kilometer usually, and if the ozone depletion resulted from the chlorine oxide cycle, the depletion would occur at middle and lower latitude and altitude between 35 and 45 kilometer. And the chlorine oxide requires oxygen atom, but in the polar stratosphere, the low sun elevation results in the essentially no photodissipation of molecular oxygen, and there is no net formation of atomic oxygen in this region. So, the above observation could not be explained by the chlorine oxide route alone, destruction mechanism alone, and depletions especially occurs in the Antarctic region during the springtime. This Antarctic region depletion occurs very fast. And also another point to be noted is when compared to Antarctic, the Arctic region where ozone depletion is, if you see some of the features of polar meteorology, we can clearly understand why this is happening there. During the winter, especially polar night, sunlight does not reach the south pole of this polar region, and a strong circular polar wind develops in the mid to lower stratosphere. These strong winds are normally known as polar vortex. This polar vortex is peculiar for this polar region. In the winter and early springtime, the polar vortex is extremely stable, sealing off all the air in the vortex from the outside. So, more or less nothing spread out. This exceptional stability of the vortex in the Antarctic region is a result of the almost asymmetric distribution of ocean around Antarctic region. And if you notice, the air within the polar vortex can get very cold, and that almost freezes out all the chemical species in the polar region into a cloud. So, once the air temperature gets to below about -80, that is 193 Kelvin, that temperature is possible, and polar stratospheric clouds are popularly called PSAs as are formed, that is in all the chemical constituents are condensed together, and polar stratospheric cloud is formed there. So, cold temperature, that is cold enough for the formation of polar stratospheric clouds in this Antarctic region, and polar winter leading to the formation of polar vortex, which isolate the air mass within it, including all the chemicals ingredient present in it. And as the vortex air is isolated, the cold temperature still persists in this polar region, and this allows the growth of polar stratospheric cloud and subsequent sink to lower altitude, therefore removal of gaseous nitrogen species. Any nitrogen compound containing species are removed from there. And the moment sunlight appears in this place, what happens is it initiate ozone depletion reaction sequence because of the photochemical process, and the solar light is very much important for this. The moment solar light appears, again the photochemical reactions are initiated, generating chlorine oxide, chlorine radical species that eat away all this ozone present in the stratosphere. So, what are the impacts of this ozone layer depletion? Ozone layer, as will be discussed, absorb most of the harmful UV radiation, especially UVB radiation, and that means what happens is more skin related disease. Skin cancer will be generated because of this ozone danger light reaching the earth atmosphere. And not only the skin cancer, even eye problem may start with this cataract related eye related issues also. Consequence of this, more UV light reaches our earth, and also it is reported scientifically the immune system is weakened. If more UV light reaches the earth atmosphere, human beings are exposed to this, and immunity is minimized is another issue. So, these are all related to human beings. Okay. At the same time, it also affects the plant kingdom, reduced plant yield. If more UV light reaches, whatever the normal plant yield is not happening. Reduced plant yield is one of the problem, so leading to agricultural loss. And also not only the plant system, even it causes damage to the ocean ecosystem. Most of this marine ecosystem things also affected because of this, and not only to the ecosystem, to the plastics also damaged because of the more strong UV light, deterioration of the plastic also happening. These are some of the impacts due to this, and ultimately we have to control this. So, the main precursor for this ozone layer depletion is CFC. This has to be controlled. So, as per the Montreal Protocol, we have almost all countries agreed to stop using CFC for cooling related purpose. All our domestic refrigerator available in the market now is CFC free. Okay. So, that way we made a significant contribution in controlling emission of CFC compound into the atmosphere. If you completely stop this any chlorine containing compounds, we can definitely minimize the impact of all these things, and we can protect the stratospheric ozone as such, a steady concentration of about 10 ppm is present. So, to summarize what we discussed, how ozone is formed in the stratosphere naturally, and what are the ways the very important ozone in the stratosphere is destroyed, especially from CFC compound or any other chlorine containing compounds, how it leads to loss of ozone, especially in the Antarctic region because of the cold climate. This brings out all of a sudden ozone hole, and that leads to lot of issues. Ultimately, we have to control, thus controlling none other than minimizing the use of CFC compounds. Thank you.